Welcome to this webinar on the clinical application of VEMP tuning measurement. I'm going to look at taking the clinical VEMP measurement and extending it into other measurement properties to investigate the function of the inner ear vestibular structures. For those of you that are very familiar with VEMP and are conducting cervical and ocular VEMP regularly, this first part of the webinar is a recap. So place me on mute, grab a coffee and a tea, and then come back and join us for part 2, where we'll be looking much more at how we can undertake that measurement quickly in the clinic. For those less familiar, it's always nice to place a clinical assessment in context so that when we start to move beyond what would be the normal use of the test, we can understand how that is being applied. So let's start with what a VEMP measurement actually is. VEMP stands for vestibular, so the inner ear structure for balance, motion, gravity and movement. It's evoked, so we need a stimuli to actually elicit a response. It's myogenic, meaning it's a muscle reflex. However, in auditory assessments, we have used muscle reflexes for many, many decades if we think about the postauricular muscle and the stapedial reflex in the middle ear. And it's a potential, so we can actually measure this activity and represent that in a form where we can look at its features. Now, sound-evoked vestibular responses in the historical context actually go back maybe a little bit longer than we maybe first would realise. In 1929, Professor Pietro Tullio introduced that concept of acoustic sensitivity of the vestibular system. Tullio's work involved the detailed observations of sound-evoked head and eye movements along with postural changes in animals. He received the Nobel Prize for that in 1932, and even now in auditory and vestibular science we refer to the Tullio phenomena for sound sensitivity in the inner ear structure. Moving to the 1960s, we've got von Beckersay, who again, one of his many achievements, received the Nobel Prize for the first reports of this vestibular response to sound in normal human subjects, and provided the first evidence that these responses were not mediated by the cochlea, and proposed that the otolith organs were being stimulated by some form of fluid displacement through the endolymphatic fluids. Now, moving more from the lab and into the clinic, we've got some significant milestones. Now, forgive me, this doesn't cover every single milestone, but the ones that stand out to us to get us to where we are clinically today. We mentioned that in the 1960s, from von Beckersay, we started to have research looking at sound-evoked muscle responses with electrodes being placed and measured on surface. Bickford recorded responses with patients with hearing loss and again provided evidence that these were not cochlear responses but were more utilising the function and sensitivity to sound pressure of the vestibular system. And in 1994, McCure and Gillian did some experiments looking at irregular firing neurons in the vestibular system of cats, and deducted that they were activated much more consistently and reliably by low-frequency stimulation. Moving then into the clinical field, around the same time James Colbatch was making the first VEMP recordings from the muscles of the neck, and these then have been developed into what we call cervical VEMP muscles or cVEMP muscles, and measured really from that big muscle, which we'll look at very shortly, at the side of the neck, the rotator, called the sternocleidomastoid mastoid muscle, or SEM for short. And a little while later, Todd et al. In 2007 developed and reported on this alternative type of VEMP recording, utilising the very small muscles around the eye, and in particular looking at the inferior oblique muscle, which is tucked, sweeps out from underneath the eye orbit. And these were then termed as ocular VEMPs or oVEMPs. Now, VEMP itself is a sonometer response. So in addition to movement, these vestibular afferents that we have can be activated by sounds of high intensity, vibration, and also electrical stimulation if that's applied over the mastoid process. These sonometer responses are recordable pretty much all the way down the vestibular spinal tract, as these are postural control and postural stability muscular responses. So really from the tip at the sternocleidomastoid mastoid muscle all the way down to the quadriceps. Obviously from a clinical perspective, we focus much more on the upper body, as we've got quick utility, and these are fast responses to be able to use in the clinical environment, and that's what we'll be talking about today. So let's just remind ourselves what the cVEMP reflex pathway is. We can stimulate using acoustic energy. This travels up the saccule, from the saccule up to the inferior vestibular nerve, into the vestibular nuclei. There is some crossover, but predominantly it's an ipsilateral response coming down the vestibular spinal tract into the spinal accessory muscle, and then being initially for us recorded from the sternocleidomastoid mastoid muscle. And that's what we do when we stimulate on the ipsilateral side to the response measurement. This is what we call an inhibitory response. So when we actually present the stimuli, the muscle has to be tonically contracted. And again, we'll speak a bit more about this later. And so the muscle then relaxes and reactivates following the stimulation. And it's that we're recording in the VEMP measurement. For preparation, what we want is some electrodes on the sternocleidomastoid mastoid muscles, both right and left. We want some sort of reference placed on the clavicle, is very convenient, and then a ground tucked away just on the head, just for convenience. And that then gives us a good recording montage to capture these biphasic responses. In the Eclipse, we've got our setup there, which can give us lots of little adjustments, but typically your standard protocol will have a lower frequency, as discussed earlier, stimuli with a relatively low repetition rate, different intensities. Now, depending on whether we're going from air conduction or bone conduction, we're still at quite loud levels to stimulate these organs, and again, we'll reference that a little bit later. We can apply some filtering just to make sure that the energy that we're measuring and concentrating on is quite clear around the biphasic and take away some of the noise. And obviously we can adjust our transducers between air conduction or bone conduction, and in particular the newer B81. Numbers of repetitions, well, again, we'll talk about that a little bit later. It really depends on the reliability of the response and how many responses we're wanting to record, and having a sufficient time to see the complete waveform over when we record in our EP system. Now, one of the key things that we will come back and talk about is EMG monitoring and scaling, because that becomes incredibly critical when we want to really utilize VEMP beyond what would be classified as the more traditional recordings. So now let's take a quick look at the oVEMP pathway. Again, this time we're stimulating either acoustically or by bone conduction, air conduction. But the pathway now is, if we stimulate on the right side, it's a crossed over response. So we're going up the superior arm of the vestibular nerve, into the vestibular nuclei, coming MLF into the ocular motor cranial nerve 3, and then measuring that under the opposite contralateral side eye in the inferior oblique muscle. So actually the response is bilateral, but the strongest response is on the contralateral side. This is actually slightly different to the cVEMP in the sense that in the cVEMP we've got an inhibitory response. This is excitatory, so the muscle actually is activated and jumps when stimulated. And again, we'll see that in what it looks like when we record that response. In terms of montage, there's been quite a few different montages in oVEMP. We know that the timeline from it moving from the lab into the clinic is still relatively short, so that shouldn't be of any surprise to us as we're developing the clinical sensitivity. But typically now what we're looking for is a ground generally placed out the way onto the forehead. We want the reference electrodes under each eye, but obviously the eye that it goes under is the opposite side to the stimulation. So if we're stimulating the right side, we want the right electrode under the left eye. That's probably the bit that catches the majority of us out, because it is a little bit back to front. So you just need to double check with that. The non-inverting electrode can be placed on the chin, or more commonly now we've seen references, particularly by Jaz Sandhu, looking at different positions of the electrode being moved away from the field, which is underneath the eye, to either the chin or onto the bridge of the nose. Optimum would be into the inner canthi of the eye, but in actual fact we can record generally quite reliable oVEMP responses placed on the bridge of the nose, and using that then as a reference for both the right and left side. Again, in our Eclipse, we've got the same sort of setup. We can adjust depending on which the stimuli we're using, and again, we're at quite as high levels as we can get, particularly as the oVEMP is a small response. And again, we'll address that in a little bit more detail as we move through this webinar. Now, what type of stimuli can be used to elicit the VEMP? Well, we've already spoken a little bit about air-conducted stimuli, both by a click or a tone burst. And those generally then are presented unilaterally and measured from the side. So here we've got an example for a cVEMP, and we can see the right and left sternocleidomastoid mastoid muscle being represented. The other option is a mechanical vibration response. So that typically could be a tendon hammer or a mini shaker, but obviously moving a bit more towards bone conducted sound as well, being more clinically utilized. And also we mentioned that electrically we can stimulate the vestibular system, so you can record a galvanic response. So we can actually use a galvanic or electric response by placing electrodes and passing a small current through them. But today we're going to focus really on air conduction and bone conduction, because we're talking about clinical application, and in the clinical setting these are the two levels of stimuli that we're more readily available to us. Again, clinically we've been using sound as a pressure stimulus, and what we need to remember is that unlike an auditory stimulation, we're using the sound to produce this hydromechanical force. Again, if we look back to what Tullio described earlier, it's to move the fluid, the endolymphatic fluid, and translate the otoliths. Under bone conduction, we're thinking this is more of a vibrotactile, and there are other factors in play, but certainly we're still looking at moving either the macular bed or moving the otocornea by moving the endolymph. And this tends to be swayed a little bit more to low frequency, as that provides the greater push of hydromechanical force. So what might we see in a typical cVEMP waveform? Well, this is biphasic. I'm sure you've seen some of these quite familiarly now. We mark them as P1, N1, depending on which stimuli you're using. That could be anywhere between P13 and P16 in milliseconds, and N could be around 23 milliseconds. But it's that inhibitory and excitatory recovery that we see represented there. Mentioned latencies, amplitude. Again, this varies between subjects, but within subjects they tend to be quite symmetrical, other than with pathology. So we're looking at much larger amplitudes, anywhere between 50 and 300 microvolts. Most commonly, we will have been using VEMP to look at asymmetry, so a bit like a chloric response or a V-hit response, comparing one otolith system with the other. And again, some of the earlier work now with Young et al. In the early 2000s gave us some sort of cVEMP asymmetry being greater than 36% as being significant. We can actually do an asymmetry calculation. You can either do this manually, or if you're fortunate enough to have a system that can calculate this for you, effectively it's applying the amplitudes from both sides and looking at the percentage difference between them. In an oVEMP waveform, you'll see that it looks a little bit different. We've got this movement down and up. So this is the excitatory part. So the N1 is now usually around 10 milliseconds, and that's the muscle actually being activated, and the P1 is it then relaxing back into its normal position at the end of the stimulus envelope. Again, we're looking at latencies that are incredibly short in milliseconds, but long when we compare them to auditory latencies. However, we will see the oVEMP amplitude typically is on average around about 7 microvolts in a healthy adult. It could be much smaller than that. With standard deviation, you could be looking at 2 to 3 microvolts being a normal bottom end measure, and probably up to around about 10 to 12 being the upper end normals. It's smaller because the muscle we're recording it from is also smaller. In terms of comparing the amplitude asymmetry, we've got Piker et al. In 2011 looking at asymmetry being around 34%. So very similar to cVEMP when you're comparing the sensitivity of one side versus the other. Now again, bone conduction hasn't really been that well utilised up until relatively recently, with the advent of the B81 being available, which now gets us up to stimulus levels, which can create a much larger vibrotactile mechanical response in the skull to activate the oVEMP. And in fact, here is an example looking at the size of an oVEMP in the same subject, both doing air conduction and bone conduction. So we can get much larger responses using bone conduction for certain measures. Now, one of the things we mentioned earlier was EMG monitoring cVEMP, so that sternocleidomastoid muscle is really critical for being able to record the biophasic response. We need adequate contraction, so some mechanism to give feedback to the patient, whether that's you telling them an auditory signal or whether they get something visually to look at. That will then only allow data in the Eclipse system to be recorded when the SEM is at the right contraction level. So it makes the data a little bit cleaner, also allows us to record shorter responses. It's sensible to then talk why we would do EMG and how we can scale for EMG. Again, I'll come back and give you an example of this a little bit later, but essentially, particularly in cVEMP, we're looking at the size of the response being relative to the muscle activity. So less muscle activity gives us a smaller cVEMP response. So therefore, if we can scale it to the activity within the muscle at the time the response was collected, that normalizes it and allows us to compare both sides much more consistently. To do that, what we basically do is take a pre-stimulation measurement of the EMG, present the stimulus, and then check the EMG again prior to the next stimulus, and do that throughout the recording, so we can have an average EMG recording over the course of the assessment. And there's an example how that would be represented. So pre-stimulation period of recording of EMG, the stimulus, the sweep collected for the averaging and applied throughout the traces that we're doing. Now, scaling can be done automatically or can complete it after recordings. Again, I'll discuss that in a bit more detail later in this webinar. And really what you're looking at is the average VEMP response in microvolts over the root mean square of the pre-stimulation EMG activity. So here's the example I was referring to earlier. This was recorded by Dr. Devin McCaslin in the Mayo Clinic. I have a similar recording from my own muscles, but his is much more enlightening, so I've took off sharing that with you. So here what we can see just by quickly looking at it is we've got right and left cVEMP response at 95 dB NHL, and the right amplitude is 348 microvolts. So that looks pretty large, really at the top end of what we think for the normal. And we've measured the root mean square EMG activity during that recording at 201 microvolts. Now we can have a look at the left side. Now the left amplitude is 120 microvolts, so still within the normal size, but obviously it is considerably smaller than to the right. So at face value, we may be thinking, well, this definitely has an asymmetry, a ratio difference, which could be pathological. But we can see that the root mean square EMG activity in that left response is actually 105 microvolts. So there was less activity going on in that muscle. Lots of reasons for that: neck turns, neck issues, all sorts of things can cause poorer EMG recordings. So rather than having to go back and reinstruct the patient, we can try to take that EMG value into account. However, if we look at that raw data, and here what we're looking at is just comparing the amplitudes from the P to the N for each side, really doing a bit of a John Keats formula just to create a percentage. Stick the numbers in that we've just seen there, so the 120 microvolts from the left cVEMP with the 348 microvolts from the right cVEMP. We got an asymmetry ratio as 49, so as we thought, just looking at that really does go beyond 36%. So again, maybe we're thinking, okay, that could be something pathological. Maybe we've got either an augmented response on the right-hand side, a larger response, and again, we can talk a little bit more in detail about what that might be, or maybe we've got an inhibited response on the left-hand side. However, once we apply some EMG scaling, what we can see here is now taking into account the activity, we've scaled these responses, and these are starting to look a lot more symmetrical. You'll see the amplitude now being represented as a ratio, so the right is 1.55, the left is 1.055. So what we've effectively done is normalize it by dividing the EMG activity into the actual size of the response itself. something that would look something like this. Again, we can then compare those, as we did previously, but with normalized values. And suddenly we see that actually the asymmetry between the two, when we take EMG into account, is actually 19%, so well within the normal range. So another key aspect of normalizing using EMG activity being critical for VEMP, particularly cervical VEMP. Okay, let's just take a moment now to stretch your legs, ask some questions, and we'll come back for part 2.